So we have seen BDD data structure, and now let's look at another optimized version of BDD, which is called reduced ordered binary decision diagram. Without this concept, BDD is almost useless. So if you look at BDD, it says basically split on variables. It looks like it will create exponentially large tree, and even if you fold it on some false and trues, it still looks like it will have a very large tree. So it on the surface it may appear it's a very inefficient representation. However, we will see that it can be optimized and there can be turned into a canonical representation, and it can be very useful to represent Boolean formula. And also in practice it has been found that finding this canonical representation is sometimes very efficient. So let's get to the definition. First definition is ordered BDD. What is an ordered BDD? If there is an order over all the variables, if you have let's say n variables, so all the variables put in some order p1 to let's say pn, such that each node, let's suppose there's a node v in your tree, then v the order, the v should appear in the order before then both of its children. Let's look at this example. In this binary decision diagram, you can see that p has to be before q, and because q is appearing, and in this case then r comes, then it should be r. However, in this path r comes before q, so it requires r to be a q. So this binary decision diagram is not a ordered binary decision diagram. We can extend this definition, and we now add another word in the definition. It's called reduced ordered BDD. So first we've introduced an order over variables. Now we are introducing a compaction idea on binary decision diagram. It says for any two nodes u and v, if they are labeled with same variable and both the children, like their low child is same, their high child is same, then both the nodes must be the same. Essentially, there cannot be two nodes in a binary decision diagram which have same label and they have same children. Then they must be same. Okay, and for each node you must have two different children. If they have same, if both the children of a node is same, then that node must not exist in the binary decision diagram. So for example, you have an ordered binary decision diagram. In this case, you can see then this is this node and this node. Both the nodes have same low child and same high child. Therefore, this is not a reduced ordered binary decision diagram. What you can do, you can merge these two nodes and obtain one node here, and call it the low node is false and the high node is true, and now this is reduced binary decision diagram. So any OBDD can be converted into ROBDD by iteratively applying the following transformation. If there are nodes u and v such that the variable label on them is same, their low child and low children are same, their high children are same, then you remove one of the nodes and connect all the parents of the removed node to the other node. In this process, what may happen is, by moving the parents and children relation, for some nodes you will end up having the situation that their low child and high child is same. Then you remove this node and connect all the parents of that particular node to its children. I mean, this whoever is the low of u. So let's think a minute why this process would terminate. ROBDD is always finite. In both the steps, you will be removing at least one node from the graph. So as this algorithm proceeds, it will be removing nodes from the graph. Either it will end up removing all the nodes, then yeah, naturally it terminates, or you will not be able to proceed anymore because none of the nodes satisfy these other conditions. Therefore, this algorithm always terminates. Now, if you think of a bit more, you will find that this is a canonical representation of a boolean functions, and that's very interesting, and it gives us a lot of interesting application of ROBDDs. So let's first prove this theorem. What this theorem says is that if I give you a function f, there is a unique ROBDD u with a given ordering. So if you change the ordering, the uniqueness does not hold. It's for a particular given ordering of variables, you have a uniqueness such that the ROBDD represents your formula f. So how do we prove it? You prove it by induction over the number of parameters. Let's suppose there are no parameters. Then there are exactly two functions, always false, always true, and they can be represented by true and false symbols themselves. So therefore you have unique representation of ROBDDs. Now let's consider n greater than 0. So let's suppose you have unique ROBDDs for functions with n parameters. Now we're going to show for n plus 1 parameter. So let's consider a function which has n plus 1 parameters. Let's create a projection function when put the first variable to 0 and 1, and obtain another function which has n variable, one variable less. Since f0 and f1 both are n variable functions, so therefore they must be representable by unique ROBDDs. That was our induction hypothesis, and let's call them u0 and u1. So what if u0 equals to u1? If that is the case, so the function f equals to f0 equals to f1. Therefore u0 represents f itself. Okay, so that's very pretty obvious. Now let's suppose we assume that there is another ROBDD which is u prime that represents the same function f. Then we will derive some contradiction. Therefore, the root of that ROBDD u prime should be labeled with p1. Please give a thought why I'm saying that has to be true. Why it cannot be some other variable? Give a thought. So if that is the case, then the low u prime and the low high u prime must both be u0. Because as soon as we project on low and high, then what happens? This guy represents the n variables, right? N variables formula. So they already have induction hypothesis says uniqueness, and we know they are u0. So both should be u0. And by definition of ROBDD, such nodes are not allowed. So u prime is not an ROBDD. Therefore, there is a contradiction. Now look at the other situation when u0 is not equal to u1. If that is the case, you construct a node which is labeled by p1, and low u is u0 and the high u is u1. Clearly u is a ROBDD because their children are different, and there is no other node which is labeled with p1, because in this system everything is labeled by p2 onwards, and this system everything is labeled p2 onwards also. So in this system, okay. So therefore there cannot be no violation of ordering of variables. So clearly it's a ROBDD. Now again we need to show the uniqueness. So therefore let's assume another u prime such that represents f. Therefore we can deduce that the top level should have been p1. Okay, so please think about why that is the case. It's not too hard to see, but it's somewhat a non-trivial thought. So due to induction hypothesis, my low u prime should have been u naught and high u prime should be u1. And by definition ROBDD, u must be equal to u prime. You cannot have a different node. Okay, so therefore uniqueness is established. So how do you do satisfiability with BDD? So first you turn a formula into ROBDD and then check if there is only one node false. If there is a one node false, then it's an unsatisfiable formula. If there is a complex BDD, then you can call it it's a satisfiable. So what is the benefit of doing go through ROBDD? So what happens in the process of building BDDs? You must have a formula tree, and you have a pieces of formula for which you build a BDD, then you compose them, you build a more complex BDD. In the process of building the BDD, if there's no point, if you're a BDD, very large number of nodes are needed, then you have your satisfiability check will be efficient. You can be lucky, and then you never find a very exponential number of nodes. However, there is no reason why it should not be the case. There are some formulas in which you may end up having exponential number of nodes. As a due to canonicity properties, ROBDD can be used as a formula store. If you create, let's suppose you have a complex algorithm in which you create a lot of formulas, and the same formula repeats again some later point, you can check their equality very easily. It's a very useful data structure to use to store formulas. And various operations ROBDDs are conducive to implementation. That means we will see soon that ROBDD's representation is done into very efficient algorithm, which allows all sorts of simple optimization that leads to very easy to use library. So what are the issues with BDDs? BDDs are very sensitive to variable ordering. There are formulas in which if you choose a proper ordering, the ROBDD would be very small, and if you choose wrong ordering, it will be very large. And there is no efficient way of detecting good variable orderings. And in fact, there are formulas in which no matter what ordering you choose, the ROBDD size will be large. So there is no free lunch in this world, and the ROBDDs work sometimes, but there are situations where they don't work.